Chen. My final project for CNCI e89 is a case study in biology. In human blood, there are different types of blood cells like red blood cells, white blood cells, platelet, and many other subtypes. And the diagnosis of blood-based diseases often involves identifying and characterizing patients' blood samples. Here I want to develop a method based on the convolutional neural network to detect and classify blood cell subtypes. The data is from Kaggle, and it's basically from this website, and it contains about 400 blood cell images and its corresponding labels, as you can see here. And let's go to the Jupyter Notebook. Jupyter Notebook to take a closer look. Yeah, basically it's from Kaggle and 400 samples. And there are 2 samples missing from the image, so I have to update the label CSV file manually. Here's the required libraries. It's quite common, nothing special. We just import libraries and we set the dir directory of the source data. And let's take a look on the dataset itself. Here's the data for the label. Basically, you have one column for the image ID and the other column for the category of that image. And the problem is, if you go to the data, you can see that the images are not named as shown in the label. So it's not 1, 2, 3, 4, you have some other things there. You have to clean it up later on. But basically, one thing you can see is there are 4 major types here, and all the others are just the minor types, which I think is too small sample size to train a neural network. So things I did is that I removed first the multiple label samples, which can make things complicated, and also remove the subtype of bus file, which only have 3 samples. So in the end, what we got is a sample size in total maybe around 350 samples. And the maximum sample size for each type is 200. Then for the mono side, you only have 20 samples. So it's really a small and imbalanced data set. The next thing I want to do is to rename and clean up the image data. First thing is to rename to align with the labels in the CSV file. And then we remove the images that were not included in the labels. If you don't have labels, you cannot use it for training, right? And this is the result. We have less than 20 images removed. And now let's take a look on the image for each subtype. Here you can see that when you color the cells, you can see that different shape. This can be a characteristic or features that can be learned by the neural network. And there are 4 types. The first one is the neutrophil, and the lymphocytes, and the other types. So the data set is imbalanced and the sample size is really small. So I tried to train the neural network based on a small sample size, but failed to get a good result. So in the end, I have to do some augmentation to generate more images for each subtypes. So this is not a perfect solution, because even after augmentation, the variance is still small, right? But it's the only choice I can have for this problem. So the target is we got 3,000 images per type. Of course, they all derived from the small sample size. And we're also going to use the image augmentation in the training steps. And here's the code to do the augmentation and put the images into different directories for future augmentation and training. So this may take 20 minutes to finish. Basically, we have an image data generator created. Then here's the target number of samples, and what's the ratio between the training and the test dataset. As here I set to 0.8 for training. And then we create the directories and move the images to corresponding directories. And here we define how many runs we should do for each image to expand the number of images. And then we have a for loop to do the augmentation and decide whether this image is going to go to the training set or test set. And this whole step takes about 15 minutes to finish. And in the end, what you have is, if you go to the folder, here is the data there. You have some original images here, then you have a train and test dataset. In each directory, you have the 4 subtypes, and in each folder, you're going to have the augmented images. So then we are ready to go for the training. And the next step going to be build the model and train it. And here's the code to prepare for data. We have an image generator for the training set and the test set, and then we decide what's the batch size, what's the target image size, and the class mode is going to be categorical, right? We will have 4 classes. And then after that, so it found around 8,000 images belongs to 4 classes for the training and another 2,000 for the testing. And then we set up our convolutional neural network model here. So first we have one convolutional neural network layer here. I have a max pole, second convolution 2D layer, max pole, the third one, and we flatten it. And we set dropout rate to 0.5. And then we have another dense layer with regulation. And in the end, we use softmax to output to 4 different classes. And then we return the model. This is the function we're going to use later on. And then we clear any sessions for previous runs, build a model, and here's the summary of that model. It's not too deep, but kind of decent size. And then we train the model with our data. So after about, I believe it's around 30 minutes, we get it done for 50 epochs. And then here's the result. Here's the training and the validation accuracy. And the validation accuracy can reach to about 80%, 75%. And here's the training and the validation loss. So we don't see clear overfitting. So from this area, maybe we don't have quite good improvement, but you can still see a static improvement here. So it looks like the convolutional neural network works. We can reach to around maybe 75–80% accuracy. So let's check what CNN sees on one image. We just randomly pick up one image here. This is what it looks like. So if everything goes right, the model should look at this area. Then I use some code from the course, basically extract output and see what the neural network are looking. And here's the result. This is the first convolution layer, and some of the filters did notice that this is the important area of the image. The max pole layer 1, convolution layer 2, and max pole 2. For the convolution layer 3, more and more filters focus on this part. So from the above activation visualization, you can see that the model correctly located the cell and its features. And I also want to visualize the filters in the trained neural network. This code also from the course. I did small modification on it, but the skeleton is from the course code. And we visualize the filters on 3 levels. You can see some interesting patterns in the filter. Now in the end, I'm going to check the focus of the CNN through the heat map technique. And first we identify which class is assigned to neutral field. Here you can see is 3. Then based on that, we can write some code to check the focus of the CNN. And so this is from the course, just with small modification. And then you can see when you plot it, the neural network really look at this area. This is the important area that contribute to the final outputs. And if we overlap this with the image, so you can see right in this part is recognized by the convolutional neural network, and this part contributes a lot to the final output. So from the above visualization, we can tell this trained convolutional neural network is looking at the right part of the image. And as a summary, let me go to the full report. Let me go to the summary one. It's good enough. The process that the lesson learned is that I spent quite a lot of time spending on cleaning and preparing the dataset. So the dataset on Kaggle actually provided you the augmented images, but I didn't use that. I want to practice how to do it by myself. And another thing I learned is that, at least in my case, the convolutional neural network doesn't work on small sample size. Even you do many epochs or do augmentation or something, it's still not working. And the pros is that this model is easy to build and train, and also utilizing the computational power on AWS significantly speeds up the development of the model. And the concern of this model is the sample size is quite small, and the lack of variance limits the performance of the model. Yeah, that's all. Thank you.